We have a next presentation. Let me welcome here Dan Kilper from the Center for Quantum Networks. So Dan is an expert in optical networks and also in the setup of QKD networks, as I understand, recently.
Recently, maybe, yeah. Okay.
So, and he will highlight to us the recent advances in the QKD network in this project CoQREATE.
Yes.
Okay. Thanks, Dan, and welcome.
Thanks. Yeah, thanks for inviting me here. I was here a couple of years ago, and I think it's a great workshop. I'm glad to be back. And actually, I'm from the Connect Center, but we collaborate with the Center for Quantum Networks. And I want to just say briefly what the CoQREATE project is. It's a great project that it's a US-Ireland project. It connects between the Connect Center in Ireland and QTech in Northern Ireland and CQN in the US. And so you can see the different universities involved there. So it brings together these large centers. And our center actually, I don't know if I would claim to be an expert in quantum myself, but and I come from an optical communications background, and I'm going to talk really from that perspective. But this project is great, and I think it's similar to the spirit of this meeting in that it brings together experts from the classical space together with the quantum space, and we're trying to tackle this problem of well, first off, creating deep collaboration between quantum and classical networking communities, but also bringing center scale research to these critical interdisciplinary challenges around terrestrial and satellite communication assisted quantum networks. And we have a number of different areas that we're looking at there. And then as part of that, we have a significant test bed actually was built up for classical networking in Ireland called Open Ireland, and involves actually radio and optical, and we're connected to dark fiber around the city of Dublin, and so we're able to do some interesting experiments there. And kind of at the heart of this, we have a reconfigurable optical switch that allows us to put both commercial and kind of prototype optical gear on this network and connect it with a bunch of test equipment, so we can do really interesting configurable experiments. And importantly, we've got 1,700 kilometers of spooled fiber in the lab, right? So that we can really set up different topologies of networks and things in an experimental sense. And recently, we've been adding, for example, quantum sources and detectors. We're getting some SNSPDs, which will be arriving shortly. And we have some dark fiber, which is our quantum outside plant that allow us to do some interesting tests. And actually, turns out that's coming from our electricity provider who manages an optical network. And so it's aerial fiber. So we'll get to try out this aerial fiber. Should be fun and interesting. And also related to this, there's another US-Ireland project called MiniNet Quantum, which is providing modeling and emulation for quantum networks, building on what we've done in the classical space and adding a quantum to it. And actually, some of what I'll talk about towards the end of this is related to this, and it also involves Bulat, who's here at this meeting as well. So I'll start out to give some perspectives on QKD systems today from my perspective, which is really coming from an optical communication systems background, right? And so the first thing that I find striking is that situation that we have where this is ADVA, actually now they're ADTRAN, they were just recently bought and changed their name, but also Nokia and Ciena, they have the same thing. And you can see in here, they've got their quantum safe connect guard encryption. And this is, I mean, QKD commercially has been around for, I don't know, 20 years or so, right? Maybe since I was a graduate student, so longer than that even. But you weren't having the big optical system vendors actually having quantum in their features list, right? And this is a hybrid we've heard about, basically PQC plus QKD together, right? And so they're offering it, and they have customers that are trialing it and doing interesting things with that. So it's getting out there in the commercial world now. And then you have, for example, well, we heard it from Deutsche Telekom, and we do a lot with Andrew Lord over at BT, and he's been talking at the OFC conference about what they've set up in London, and it's supposed to be a QKD network that has customers in the London area who can set up to secure their links over this QKD network. So it's starting to get into that space as well, and that's part of the reason, obviously, that those optical system vendors are actually offering these commercial systems. Now then, we've heard a lot about IDQ and Toshiba. There's kind of the two main vendors. Of course, there's a whole host of startup companies and other vendors that are emerging here. And generally, you get a few hundred kilobits per second at about 10 dB loss. You can go up to around 100, 150 kilometer reach. And the C band is your main communications band, optical band, and also the S band is another one that is used a lot. And then and key management can be built in or separate. And so these are nice rack mountable boxes, but still the system vendors that ADVA system that I showed before, they would do classical encryption and key distribution. So they would have their own key management system that they would offer to customers, and they would have it built into their line cards and into their hardware, right? But the QKD now is a separate 1 RU, which is actually a significant rack space compared to a board that's going to get inserted into their system. So this is really kind of an external add-on thing for these systems. In the future, that has to move onto the chassis into the pluggable board and become an integral part of the system if this is going to continue and have life, right? But what I want to talk about is kind of where do we go next? Okay, so that's where we've come to, and I say where do we go next from an optical system and networking point of view in terms of developing this technology, because fundamentally QKD is an optical system technology, right? And one path that we can take is the traditional system evolution path from what we have today are connected devices. I put them on the network, I can have them talk across the network, that's fine and good, but how do I make a truly system, end-to-end system approach to that? Now, I would argue also that we're kind of working on a lot of the system aspect of that, and that's where the key management and so forth comes in. But it's still a little bit ad hoc in developing at this point. But eventually, we'd like to get to networks, right? We should be able to construct networks of QKD in our fiber networks. And so we need to add switching, multi-hop control and management, tunability, all of these sorts of things that we don't have today. The other approach that we can take is to, well, that would be kind of traditional system evolution, is increasing capacity, right? So in optical communication systems, we spent generations after the first fiber optic communication system was out there. We spent the next 2 decades making it, adding wavelengths, making the transceivers faster. So here, boosting secure key rates, doing some sort of multiplexing. How do we start multiplexing with this and really getting the capacity up, right? And then the other big thing that we work on traditionally is reach, right? So how do we go longer distances? And obviously that's really important here. So a lot of people are concerned about that we can only go 100 kilometers. How do we get that out to thousands of kilometers, right? And then and that'll involve repeaters or multi-hop type technology ultimately. And then the other thing is, of course, increased reliability, which goes along with that. Now, with quantum, there's a couple of other directions also to evolve these systems. One is classical coexistence, right? So all the QKD systems today are add-ons. They're separate systems that use their own separate fiber pair. They don't even go in the same fiber as these classical WDM signals. And then, so can we integrate them with classical communication networks? And there's a number of challenges there, but people are looking at that today, and there's been experiments. And then there's what I call the classical add-on, which is not just coexisting, but trying to kind of integrate it as a feature within the network. And I'll show you some examples of what I'm talking about here, but really trying to enable the quantum to use a similar a networking environment as sort of an add-on to the classical system. And then this is what I mentioned before, including it really as a line card or a feature in any optical communication system. So it becomes part of that supply chain and part of that ecosystem. Now, there's a long history, as I mentioned earlier, of QKD field trials, and even BT was doing things in the 1990s. Now, currently today, many people are familiar with the big network in China, which has received so much attention, right? And we heard several people talking about Euro QCI here in the EU, where we're trying to build up an EU-wide QKD network. And so we've got a lot going on there. Now, one of the things that I find really interesting, though, is this transmission reach race that has emerged in, I don't know, the last 5 years or so. And so people have really been trying to push the envelope in terms of how far can you get a QKD system to really go. And this is exactly the sort of thing that we need in the research space to move the technology forward. And so there was reports going out. What was it? So 140 dB loss or 834 kilometer QKD transmission, and that was in. I have the data. That was the 2022 result that I've referenced there. And then 2023, another group comes out with actually 157 dB loss, 1,002 kilometers, right? Which is amazing, and it's fantastic. But of course, if you look, I think this is the result that went out over 1,000 kilometers, and they're getting 10 to the minus 10 key rate per pulse, right? Which, but that's okay. It's a hero experiment, right? And the point is that, okay, so you push the technology out to this corner here, but you're going to use the technology back here. And by the way, that's what we've been doing with classical systems from day one, right? So the hero experiment is always way beyond what anyone deploys, right? But the point is that it's actually bringing these new technologies to bear. And in fact, later in 2023, another group said, oh, well, look at how low those rates are. We need to focus on getting the rates up. And they came out with this new PMP QKD technique that gets you up to 5 kilobits per second at 300 kilometers, which actually is really, really impressive, right? You could start to work with that. And so this is the type of kind of research race that we need in terms of traditional capacity and reach scaling for these types of networks. And the other thing that we need to see more of, and this is something that we're working on in Dublin, is to get some of these systems and look at how we're going to engineer them in terms of engineering rules. And so if you have a secret key rate or a quantum bit error rate, you'd like to know what your margins need to be. How do you set your margin? So, and you always need some sort of margin between that kind of fluctuation that happens all day long over time and kind of the minimum secret key rate that I need, right? And so you need to understand how these systems will vary under different conditions and really then how to engineer that and account for that, and even establish where you are relative to that margin in a real sense. And then you've got network aging, you've got other things that you have to account for in your engineering, and we're just getting started on understanding all of these kinds of things. And then we need different types of metrics, and so a lot of people talk about the rate times distance product. And actually, if you look, I mean, really, we're always plotting the log of or on a log scale, the rate versus distance. And so probably the log of the rate times distance. And if you're doing coexistence, so the power of the classical channels is another interesting one to include in there. And we need to look at these metrics and understand how they impact the engineering and whether it makes sense to go with one or the other. So that's kind of one of the directions that we're going. I mentioned this add-on approach, so let me just say a little bit about that. One example is to integrate the QKD control into the SDN environment that we're using classically. And that's now being done by a lot of the commercial system vendors as they start to include QKD. And some of the early work in 2019, early now, University of Bristol was showing an SDN controller that's kind of monitoring and working with an IDQ system and responding to events that happen on the quantum system. The other thing is, well, in the classical world, there's a lot of interest now in moving to hollow core fibers, right? And so you could imagine when you have hollow core fiber, well, you could integrate your QKD and have it coexist with the classical signals in the hollow core fiber, because there is no nonlinear effect. The scattering is low. And this was an experiment in Bristol and Southampton now, where there was no interaction between this QKD system and the very high capacity classical system going through the hollow core fiber. And hollow core fiber also, just this past year, it surpassed the loss. In other words, got lower loss than standard single mode fiber for the first time. And they were able to get below 0.1 dB per kilometer, where standard single mode fiber is normally around 0.2, and the best standard single mode fiber is kind of 0.16 or something, right? So that's significant. They believe that they can even get as much as 10 dB below, and they can also move the wavelength window of this fiber down to 900 nanometers, 800 nanometers, something like that. So it could start to be compatible with a lot of these quantum memories and so forth, which is interesting. And then another direction that the classical world is looking at is going to these multi-core fibers. So you have multiple cores within the same fiber, essentially a very compact cable. So not all that interesting, but now if I'm trying to integrate quantum and classical together, maybe my quantum is just going down one of these cores, and I put my classical signals down the others. And a number of groups have looked at this, and including Toshiba and Cambridge, and show that that works. Okay, but now what we're most interested in is the evolution towards the networks and what's happening there and the potential for that. So there's not a lot of work in terms of switched QKD systems. These QKD systems, they're designed to have a compatible pair. They sell them in a pair. They talk to each other. There's a lot of tuning and stabilization going on there in terms of the kind of parameters of the system. It has to be at the same wavelength, and there can be long time delays to get that up and stable. So there was this result out of China where they actually did some optical switching in the star configuration. They didn't really report a switching time. It looks like they just kind of switched and waited for the QKD systems to restabilize and work, right? So very slow timescale switching, but there really isn't a plausible approach to optical switching in QKD systems, in these prepare and measure QKD systems that I've heard so far. But an interesting spin on this actually is to go to MDI QKD. And MDI naturally has this kind of central measurement device independent node that all of the different end nodes can talk to. And you can have more than just an Alice and a Bob. You could have 5 or 10 different nodes that all communicate to a central MDI node, and they can then share keys or develop QKD between the different nodes, and you can effectively implement a switching type of approach with MDI QKD. The other, and so this was out of QTech group in the Netherlands, and they've actually spun out it's called QBird, a startup company that's commercializing this. And so the other interesting approach is to use entanglement, right? And there's this nice work from the Austrian group looking at, if you take a spontaneous parametric down conversion source of entangled photons, right? So it's going to put out photons in a broadband sense. So you can center this is in the middle of the C band, basically. And so you're going to emit photons all through the spectrum here. And generally, you're going to get entangled pairs that are symmetrically located about the center of this distribution pattern. And so you could pick out these symmetric pairs and then send them through the network. And what they realize is that, well, there's a clever thing you can do here. We often have sort of wavelengths like the filters or switches that we can use. And now we can use that filtering to select different pairs to go to different end users and kind of create a star network. So you have your source in the middle here, and it can send to the different end nodes of this physical star network and create entanglement between each of those nodes. And then you can build up actually quantum correlation and therefore use that for QKD between any of these end nodes. And this is especially valuable for QKD, and I show it using QKD because you need this filtering. But at the end of the day, you don't care what wavelength you're coming in at the end, at the receive side, right? So in other words, you're not trying to match it into a memory, for example. If you have to couple your light into a memory, then you have to match the wavelength of the memory precisely. But in this scenario, you can just do QKD with whatever photons arrive, or analyze your polarization and get your result. And that works great. And so they showed this. And then also there's the Bristol group started working with this and actually has done many different experiments where they've shown this kind of star configuration, and they've done coexistence with many types of classical signals in that type of configuration. And so they, for example, this is their photon counts as a function of frequency here. And so they divide up their spectrum, and then they can send different portions of the spectrum to different nodes. So you can actually allocate more of the spectrum to one pair of nodes that needs a higher rate, or if there's a pair of nodes that are farther apart, so you're going to have a lot of loss on that link, you can, again, take a bigger chunk of spectrum to make up for that with this kind of multiplexed distribution of your photon pairs. And then you can basically create whatever topology. Here they're showing that you could do a complete mesh topology between these different end nodes in entanglement space, right? And your entanglement kind of creates this virtual network that's independent of the physical topology, effectively, of entanglement between any two pairs of nodes, right? And then there's various assignments that you can do of the wavelengths here, first fit, split spectrum, and different things that you can do. And so we were looking at that and thinking about, so how do we make networks out of this? And especially thinking about this kind of add-on approach where we have this infrastructure in classical networks. Actually, there's something that we call a ROADM, which combines wavelength selective switches and various fiber splitters and combiners and things to create a node where you can take any wavelength coming in on one fiber and send it out on any other fiber. Here I'm showing an example of a 4-port or a 4-degree a ROADM. You have fiber pairs on each of the inputs and outputs, and you can send any individual wavelength in any direction that you want. And you can have degrees up to 10 to 20. So you can have many, many different inputs and outputs here. And they've deployed thousands of these ROADMs over tens of thousands of root kilometers. Now, in general, you have amplifiers all over these, right? So if you're going to put quantum in there, you have to bypass the amplifiers. And you could do that. And the technology, although it's built up right now in the C-band, they're starting to make switches and things down at 1300 nanometers and so forth. So you could run your quantum down at those wavelengths as well, or you could run them through hollow core fiber or multi-core fiber, right? Now, one of the interesting things that comes up if I'm trying to route my optical signals through, for example, here's a 6-node network. Basically, I have signals going from 1 to 6. I might deploy a wavelength along that path. Now, one of the things that we have to deal with is once you set up a wavelength from node 1 to 6 through this network, that wavelength is occupied throughout that portion of the network. So if I want to add another signal between 3 and 5 at the exact same wavelength, it's not going to work. It's blocked, right? So we call that wavelength blocking. Now, if you have 100 wavelengths, I just move my wavelength over to a different wavelength. It's fine. I don't care. But in general, you fill up your capacity, you start to get a fragmentation across the spectrum. And so this becomes an issue. And so now there's a design problem. How do I optimize the routing of my wavelengths through the spectrum? Right. But what's interesting, if we think about this now in a quantum context, right? So I have a network here, and I want to do QKD between any two nodes within this network. And let's say I put an entanglement source at node A here, right? And so nodes B and F on this network want to be entangled, and they want to be entangled at some certain rate. And then I'm going to basically try to distribute that entanglement from node A. So I send my entangled photons along the path A to B, and then A, C, E, F, right? And so actually, I'm not sending any light directly between B and F, right? But I'm entangling B and F. So my routing problem is really a strange routing problem compared to the usual one. The other thing is, of course, photons don't care if you kind of direct them through each other, right? So you can actually just use a single fiber to do the routing. We don't need two fibers to do full duplex. So I can do bidirectional within the same fiber, which is kind of unique as well. The other thing that's interesting here is that there's a number of different ways that you can set up this SPDC source. You can do what we call an unheralded approach, which is what I described in the first sentence, where I just get these pairs symmetric about some center point, and I need to distribute them using some wavelength selective switch. But I can also do this approach that folks at the University of Arizona and MIT came up with, where they have two SPDC sources. They essentially do a swap, a wavelength dependent swap from the two sources. So the idlers come into the middle. If the idlers match up in wavelength, you do a Bell state measurement in here, then you get entangled signal photons at the same wavelength. And what's interesting here now, I've got some neat animations I'll run through really quickly here. So what we can do with this is now, in one case, for the single SPDC, right, you're at different wavelengths with your pairs. For the dual SPDC, it's the same wavelength. So now you need disjoint routing through the network to make that work. And so you're taking slices of your spectrum and then sending it around the network and trying to create entanglement. And so here's the little animation to show you. And then there's a whole bunch of interesting problems that you can look at in terms of designing these types of networks. You have to deal with qubit loss, qubit noise, and then synchronization and control in order to manage this overall network and make the network work. And so we're looking at different elements of this. And in general, the problem that we first started to look at was this wavelength routed entanglement distribution. And so we've developed various architectures, node architectures, using these wavelengths like the switches so that you can make networks out of this. I'm running out of time, but I want to talk about, so this is work in collaboration with Bulat and his student Rehan had a really nice paper at ICC here, where basically we showed that we can look at this problem and look at how we would slice up that spectrum in order to satisfy whatever demand we have in the network, taking into account the loss between the source node at A and any of the end nodes where I'm trying to create entanglement. And what he showed was that, well, first off, we looked at a number of different ways of now assigning that spectrum. You can use round robin, the first fit. It also turns out that this is the same problem that you have in this was it the uniform machine scheduling problem. Now, when you're trying to schedule machines to process some job, you're not trying to get the maximum of, say, your minimum pair rate or something like that. And instead, you want to minimize or you want to most efficiently use those machines for their processing. And the processing time of the machines is equivalent to the loss or of your channels in this problem. So anyway, you can map it on to that type of problem. We looked at a number of different algorithms. We don't have time to go into it here. We applied it to this Manhattan topology, which is kind of a metro scale topology, looking at different types of loss. And we showed that actually with the modification of the heuristic for this machine scheduling program, you could very efficiently route around the network and get something that's close to optimal. And it turns out that if you're living in Manhattan and you want to do quantum key distribution, you want to get property in the Upper West Side for this network here. Let you know. Okay, so anyway, so there are important research directions emerging for quantum systems and networks applied to QKD or QKD networks. This SPDC-based entanglement distribution, I think it's a promising direction to enable kind of wavelength multiplex networking. There are experimental realizations already, and it's a rich research space of unique optical routing and spectrum allocation problems for QKD, as well as more generally for entanglement distribution. We were talking about quantum internet earlier today. And we showed that you can optimize the source placement for this degenerate or dual SPDC entanglement distribution-based networks. Okay, and thanks for your attention.
Dan, thank you for the talk. What is the attenuation of these ROADM central switching setup?
Yeah, so they actually we looked at a couple of different losses because it's interesting. Depending on which wavelength you choose, okay, the loss will vary from about 3.5 or 4 dB up to say 7 or 8 dB. So it's actually wavelengths like this. So we looked at the two extremes. We didn't actually try to model our own. That'd be an interesting next thing to do. Because we have them, we can measure that. We can actually use the real characteristic, but it tends to be in that range. Yeah.
Okay, then let's thank Dan again.